Video, we're going to go over a statistical analysis called Logistic Regression. So I've already set my working directory, but if you haven't, go ahead and set your working directory in case you're new to this, which you shouldn't really be at this point, but just in case you are, you can go to the Session tab, set working directory, choose directory, and then choose or direct yourself to whatever folder that you are working with and select that folder. Okay, so and then all of these packages you're going to want to install. There's a bunch of them: Survival, Stringy, HMIS, Mass, RMS, popbio, visreg, presence absence, air.part, tree, popbio, oh I already said that one, and proc and IRR. And there's also some functions that will be sourced, and if you don't have these already set in your working directory, you can source most of them from this website here. It's a cornell.edu from their TeachR site. Okay, so while you're loading your packages, I'll explain a little bit about logistic regression. So this is a statistical test that involves a categorical response and a numerical predictor. And more importantly, the response is a binary categorical value or variable. So logistic regression is a type of generalized linear model that's used to predict a probability. And what makes it different from a linear regression is that it assumes a binomial error distribution. In other words, the y values are bounded by 0 and 1, so that you are computing the relative probability of getting a 1 as x values change. So for example, how does the probability of presence change as elevation increases? So the function for probability that we're going to be using is, well, the general probability formula, where probability, or your percent for probability or decimal for probability, is equal to P of I, or the probability of some event happening, divided by 1 minus P of I, or 1 minus the probability of it happening. So you're basically taking the probability of an event occurring divided by the probability of it not occurring. Okay, simple math. So we're going to start with this Polis data set that came from a study by Polis et al. In 1998. So what we're starting with is a simple single logistic regression where we're just using one model. So it's pretty easy. So we'll load the CSV, check out what the data looks like, bring up the summary, and then you can use this function to get the actual group sizes. Okay, so now we're going to fit the model. Like I said, we're going to make a single model. So this is the only model that we're going to end up working with for this data set. So what I'm doing is creating this new attribute called model1, which is a generalized linear model, or GLM, of this response variable PA, which is presence or absences, and a predictor called PA ratio. So when you're setting this up, make sure your data equals the name of the data set you're working with, and you're going to have this line of argument where we're setting family to binomial because our response is binary, and we have this link equals logit function which codes for the logistic regression. So let's pull up the summary and see what we have. Okay, so what we're given, so we have the estimate standard, the error, z-value, and then the p-value based on that z-value. And the z-value is the test statistic. So it looks like many of the output that we've had before. So PA, which is the response we have, there's a significant negative correlation with PA ratio. That's this predictor variable. And that's divulged because we have a significant p-value that's obtained. And it's significant because it's less than 0.05. And the intercept for PA ratio, which is this estimate standard value, is a negative value. And that indicates a negative correlation. So therefore, for every unit increase in PA ratio, whereas that PA ratio increases, the likelihood of presence decreases. So you can also use the estimate standard in another way. If the coefficient is less than 1, then the odds are decreasing. If the coefficient is greater than 1, then the odds are increasing. Okay. So now that we've examined that, I tried making the text bigger, but now I have to keep toggling back and forth, and it's a little annoying. Okay, so we're going to make a plot. So here we see a beautiful logistic regression curve where you have this kind of sigmoid curve that's occurring. So it illustrates the negative relationship that we just previously found. And the red dots here, these indicate predictions or values that are predicted to occur. And if you notice, there are 2 lines of white dots, and those are representative of our binary response. So that's what when you hear somebody saying a binomial distribution, that's what they're referring to. You have a long distribution here and a distribution here. Okay, so we can also run this logi.hist.plot, basically meaning make a plot of the logistic regression and show the histograms for that, the binomial distributions. So that's what I was saying before, so you have a distribution that's occurring up here, and you have a distribution that's occurring up here because we have a binary response. So here's the distribution or the histogram for our ones, and then here's the histograms correlating to the zeros. And then here's our logistic curve. Okay, so now that we have our model and we've kind of visualized it and understood the relationship, we need to actually test how well this model fits. So essentially the goodness of fit. So we can do this with, well, a goodness of fit test, which tests the observed values versus expected values. And there are several tests that can be employed. So one of them is the Hosmer-Lenishow unweighted sum of squares test, and that's like a global a global goodness of fit test. So that's what we're going to do right here. Okay, so the null hypothesis of this model is that the model fits. So you want a large p-value because that indicates that there is not a significant difference between your observed and expected values. So the output we get when we look here, we have a p-value that is much larger than 0.05. So that means we have a large p-value, which is great because then we fail to reject the null, which means that we do have a good model, or we have a model that is that fits well. So you could also run a Pearson chi-square goodness of fit test. That's another way to evaluate model fitness. If you run that, okay. So here's the output that we're given. And this is basically the amount of deviance that is explained. And so that number ranges from 0 to 1. And you want something that's closer to 1. That indicates a better fitting model. So the number we have here, 0.65, is pretty close to 1. So that means a pretty good fit. So sometimes with logistic regressions, in the end, you'll end up running a linear regression. And oftentimes, well, for me, often I would do this to get the R² value to see how much variance this model is accounting for of the total amount of variance or in the total model. So you can run this if you want. It's not that it's mandatory. So you get what we're seeing here is the same results that were obtained when we ran the initial model with the GLM model, the generalized linear model, and it's this significant negative correlation between PA and PA ratio. And so we can plot it, and so we see this familiar 2x2 matrix of these residuals versus fitted or residuals versus leverage plots to test the normality distribution of the residuals and see how well the model is fitting. So if we were doing a linear regression or in the means of linear regression, we'd say, well, it's great based on the Cook's distance, but I'm not really liking how it's looking up here. It's not really following this the straight line there. It's kind of deviating from that, which is worrisome. And it does not, I mean, it has a low p-value, which means we failed to reject the null, which means for normality testing, it's not normal. But again, this is something that you don't have to do because this is going into linear regression. What we're talking about is logistic regression. So it's kind of, it's not alarming to run a linear regression after completing a logistic regression and go through the whole thing and get these abnormal results because, well, the model is better represented or better suited for a logistic regression model. But what we can get that is of some value is this adjusted R² value. So that tells you the percent variance of, or I should say, how much this model accounts for the total variance of the whole model. So right now, this model, just PA as the response and PA ratio as the predictor accounts for 35% of the total variation. Okay, so that's a simple or single logistic regression. So now let's run a multiple logistic regression where we have multiple competing hypotheses that we want to examine. So we're going to use this Bolger data set, and we'll check out what data looks like, all that fun stuff, get a summary of it. And then we're going to build our, what I'm going to call the original model, or the initial model, which has the predictors that we want to examine in just a simple generalized linear mixed model. Again, make sure you have the family set to binomial and the link equals logit, or logit, either one. I don't think anybody really cares. Okay. So here we can interpret the outputs immediately. And we can see that the only one that has significance is right here. So that's the percent shrub, or per shrub, which has a significant p-value at 0.018 or 0.02. All of them have positive correlation. So what you can say is that distance and age have are positively correlated with this rodents P, and this is the presence of rodents. So the presence of rodents is positively correlated with distance and age, but not to a significant degree. However, the presence of rodents is significantly positively correlated with percent shrub. I think that's about it that you can say of that. So with that positive correlation, what you could say, so taking the per shrub, for instance, you could say that since there's this positive correlation, for every 1 unit of increase in X, the probability of having rodents present increases. So if it was negative, which it's not, but let's just say that was negative, we would instead say for every 1 unit of increase in X, the probability of having rodents present decreases. So just in case you were having trouble understanding that before. Okay, so we can start plotting some of these predictors with the response variables to get a sense of the relationships between them. So we can do this using the log.hist.plot function that we had used before. So this gives us, again, a sense of the direction of those probabilities or those distributions. I think for this one it was actually showing negative relationship, which is interesting because I don't think I got a negative relationship before. I think they're all positive. Yep, they're all positive. Okay. But anyway, so you can see the direction that these are moving. You can also see that this is a definite logistic regression, that you have this S-curve that's occurring and you have like a clear histogram at the top, uppermost and lowermost areas of your y-axis. So you could also simply just use the plot function to do the same thing. So here you see the defined binomial or your binary response. And in order to, so I like the log hist because you can actually see the histogram. So you can actually see kind of the distribution that's occurring for your ones and for your zeros. Here you kind of have to look at the spread of them. So by having all your little points spread across the x-axis as they're seen here and kind of a little bit here and here, that shows that you wouldn't have that clustering, which you kind of want here. You want something like this where you see a lot of your zeros at either the left or the right and your ones at the left or the right, so that you end up getting that S-curve. Here you would just get like a straight line. Here you get, again, that nice S-curve, if that makes any sense. Okay. So now we actually have to figure out what predictors are most important to our model, because we have this original model with all these predictors, but what combination of variables or what variables alone actually produce the best model? Well, it's time for model selection. So we're going to do a stepwise selection using AIC, and you can either do forward, backward, or both, whatever your choosing is. So I'm just going to run a forward. And then remember, for your stepwise selection, when you use AIC, you want to choose a model that has the lowest AIC value. Okay, so I think it's going to be, yep, this last model. So the best model here is when you just have the percent shrub alone as a predictor. You get the lowest AIC of 24.05. So you could also perform the all subset test, which takes different combinations of predictors from, I think it just takes it from the backwards model. And again, the model with the lowest AIC is the best. So let's run that. And you have to actually create your Y and X values. And then you can do the all.subsets.glm function. And you're going to have your goodness of fit set at the, that's what I'm assuming this represents, at the log like. Actually, I know that's what it is. Okay, so again, usually the first model that shows up is going to be your best model. This model definitely is the best. First of all, it has a delta AICC, which is your basically another derivative of your AIC value is 0, and then your lowest AICC value is 24.6, which you get from just having per shrub alone. So now that we know, actually before I'm jumping ahead, sorry. So say that we had all these pre-selected hypotheses that we wanted to compare, or we were interested in seeing how each of those variables influence the model. So what you could do is you could construct models of your pre-selected hypotheses, which I've built here. So let's pretend that I had this pre-selected hypothesis that maybe there was this influence of per shrub or the per shrub and age, and then this here, which I think are the only 3 variables. But anyway, you get the point. So you can test, if you have this pre-selected hypothesis, you can create competing models to test that in such manner. So we could also add in this argument to code for the AIC by adding $AIC to the end of the models. And that will give us the AIC for each model so we can evaluate it right then and there if this decides to work. Okay, so I don't know why this got all angry at me. But anyway, so you can do it that way, or you could also fit a series of competing models as so, using the same function, but you're just not doing the $AIC. You'll end up doing that later. So you can create your competing models. Oh, I know why, because I didn't change this. So in the old data set that I'm using this from, we ended up standardizing the variables, which is something that can be done if you have like a huge skew, if you get like a huge number of zeros and like 4 1s. You can standardize them so that you can kind of, you're more along the lines of analyzing apples to apples. Okay, so there we go. Okay, and then this one I added a square term to, and this is what you do when you want to test for quadratic terms. So we'll get to that in a second. But then you can test for the AIC values for each. So you plug in the model name that you gave the attribute and this $AIC, and you can get the AIC for each one. Okay, so the lowest AIC is right here, and that, oh look, it's our shrub again. So all of the models that we've run so far, all are synonymous in the thought that percent shrub alone is the best model. So we're going to run with that. Alrighty, so we'll rebuild a model of just percent shrub alone. So we're going to create model.shrub, which is our new attribute, and that consists of a generalized linear model that's testing the presence of rodents compared to the percent shrub. And again, the family is binomial because we have a binary response and link equals logit or logit. Okay, pull up the summary so that we can begin interpreting some of the output. Okay, so the percent shrub produces a p-value that is significantly less than 0.05. And based on its estimate standard, it has positive correlation. So percent shrub has a positive correlation, or rodents presence, or the rodents being present, is positively and significantly correlated to percent shrub. You can also look here at the difference in the null and residual deviances. So the difference in deviance is 19.121. I'm doing that right off the top of my head. And the difference in parameters, looking at the degrees of freedom, is 3. Since the difference is since the difference in deviance is higher than the parameters, this suggests that the current model is significantly better than the null model. So that's another way to test that, which is pretty cool. All right, so how does it actually fit? That is a good question. So let's examine. All right. Those were just some other outputs that I wanted to run. Okay, so for well, we can actually start looking at how it fits up here. So there's definitely a logistic regression, and again, this substantiates what we said previously, that there's this positive correlation between rodents being present and percent shrub. And then this function that I kind of just blew over, we'll get back to in a moment, but this is a great medium for testing model success based at different thresholds. So evaluating model fit. This is where we can start using some other handy goodness of fit tests to evaluate the fit of the model, or this model in specific. So for instance, you can use this logit.plot.quad. And this allows us to use predictive power. So basically, by having this predictive power, it enables you to evaluate model success at a certain threshold, which then lets you observe the errors in prediction. So you see these two measures down here. You have sensitivity and specificity. So sensitivity is the fraction of observed values that the test correctly identifies as positive. So sensitivity is basically your true positives, or your percent of true positives, while specificity is the proportion of true negatives. So the closer to 1, the more sensitive or specific the model. But you also want a balance of them. So you don't want like your sensitivity to be 0 and specificity to be 1, or vice versa. Yes, there will be some cases where you do want that, depending on the question that you're asking. But oftentimes you want a balance in your model, because you do not want something that is going to give you a ton of false positives, especially if you're doing a medical test. So while it might be great to have a sensitivity of 1 and a specificity of 0, oftentimes you want a balance. So in that case, you're never going to have like specificity of 1 and sensitivity of, or sensitivity of 1. You will never have that. You need a balance. So again, the closer to 1, the more sensitive or specific the model. And by default, this threshold, and by threshold I mean this dotted line here, it actually forms this crosshair. By default, the threshold in R is set at 0.5. However, you can manipulate this threshold setting, and that can be done by adding an argument. Just add it here. So what you'll do is you'll add comma threshold equals, and then whatever you want to change your threshold to. So let's say I wanted to change it to 0.6. So we could do that and see it changes your threshold level. And this comes in handy when you have a model that, say, your logistic regression curve occurs way down here. Well, obviously, it's not going to be well suited for a threshold of 0.5. It would be more suited for a threshold occurring down in this area. So the threshold can be mediated depending on the individual characteristics of your model. So it can accommodate that. Okay, so AUC tests. They're also excellent models for evaluating the fit. And when I say AUC, AUC stands for area under the curve. And it uses sensitivity, specificity, and kappa for values at different thresholds. So it's essentially a metric of how good your model is at predicting things. So we can do AUC testing using this. Well, there's actually two functions we can use. One is this AUC.ROC.plot function. So we can run that. Or this AUC with the internal ROC, and then actually plot the ROC. So let's go over this AUC.ROC.plot. So this gives you all of the information you need at once, which is fantastic, and that's why I like using it. So the x-axis here is your sensitivity. Again, sorry, specificity. So remember, specificity are your false positives. Your y-axis indicates sensitivity, or your true positives. And what's produced is called an ROC plot. So in order to interpret this, basically the fundamental thought is the curvier your line is, or the farther it curves from the straight line, the better your model. So what you're looking at is this line here in comparison to this straight line. So the more curved this dotted line is from this straight line, the better your model, or the better the fit. For AUC, the closer the value is to 1, the better the model. So here we have an AUC of 0.89, or basically 0.9, which is fantastic, because again, you want something that's closer to 1. If you have a value of 0.5, your model is useless. If we got something like 0.6, that would represent a poor model. But again, it also depends on the context of your study. In some environmental settings, it might be okay to get away with a model that's relatively poor, or not as good of a model. Okay, so that's this ROC plot. You can also do this AUC with the internal ROC argument, or ROC function, sorry. So this gives us, again, basically the same AUC value, and then you can plot the ROC. And again, the more curved this line is away from this straight line, the better your model. If this line was like right on top of this line, that would be a really crappy model, and we would be very, very upset. Okay, so now we can test kappa. And that's, again, another metric of how good your model is. So you can actually create this new value for kappa by doing such, and examine the goodness of fit from the kappa value produced through such, or you can calculate kappa through an actual function called kappa, which is a little easier to do. So this gives you your kappa value based on whatever threshold you have it at. Now this is set at the default because it doesn't contain the argument. So this is the kappa value set at the default, which is a threshold of 0.5. So here we can also create presence-absence histogram of it. Okay, so this presence.absence.hist function, it produces a histogram of predicted possibilities where you have these interesting looking bars. So these bars are subdivided by observed values. And it also includes this option to mark several types of optimal thresholds along the plot. So you can change your threshold level. So for instance, we're going to rerun this logit.plot.quad function, but say we wanted to set it at a threshold of 0.6. So we're going to do that. All right. So now we want our kappa value to be representative of such. So we can do that by adding this argument, threshold equals 0.6, the same argument that we add to that logit.plot.quad function. So we can calculate the accurate kappa value based on that threshold. So you can mediate threshold to better evaluate model success, and you can also mediate kappa in response to mediating your threshold, which I find all interesting, of course. Okay. So you can do all those fun, funky tests. They're really cool. But if you wanted to be kind of like go down to the simple times, whatever you want to call it, you can just do a good old unweighted sums of squares test for goodness of fit. So we'll run that right here. And again, for this, you want a p-value that is greater than 0.05, which we have here. And that means we fail to reject the null, which is good for testing goodness of fit because that means we don't have a significant difference between our observed and expected values. Okay. So there's this thing I had mentioned before called a quadratic term. If you had remembered, I'd bring it up right here. So in some models, you'll end up getting, when you're testing that initial logistic curve, you know how on some of them it looked like we had just a straight linear relationship rather than that nice S-curve that's indicative of a logistic regression? Well, sometimes you'll get a model that starts forming this bowl-shaped or a bell curve kind of. And that's indicative of what's called a quadratic relationship. So in some models, it's good to test for this because they're underlying and you don't really see them, or you just get a glimpse of the initial start of a quadratic relationship. So testing for quadratic terms is something I always heavily stress because sometimes it makes all the world of a difference to your model, and sometimes it does nothing. So what you do to do that is you use the generalized linear model function, but you add this interesting little bit of coding to the function. So what this is doing is saying that I want to take this distance predictor, and I want to include the quadratic term of that distance variable. So you do I and then parentheses, whatever your variable is, squared. And then you add that in addition to the regular variable to the rest of the variables that you're testing. So we can test that. Now say we wanted to see if, just put it right here. Oh, I did this stupid thing again. Okay, so say you actually wanted to see if this quadratic term, so here maybe you get, oh, we do get significance. So we get significance here, but is this model any better than the original model? Yes, we may get significance here, but it might not be any better of a model. So what you can actually do is compare this new model with the original model that did not have that square term in it. And you can do this using the ANOVA function. So we'll run that here. Okay, so you're probably thinking to yourself, well, how the heck do I interpret this? Well, it's very, very, very simple. All you have to do is look at the good old p-value. So here we do not have a significant p-value, which means there is not a significant difference between the original model and this new model that now has this square term in it. So in other words, the addition of a square term or this quadratic term does not significantly influence the original model. So if we had gotten a significant p-value, that would mean that the addition of that quadratic term significantly influenced the model, and therefore that the inclusion of such was significant to the model. So if you got a significant p-value, that means you would want to go with that quadratic model. But since we don't have a significant p-value, basically the inclusion of that quadratic term is useless. It's not significant whatsoever. So with that said, we can disregard the quadratic term. But there's also this thing of, okay, so we figured out the nature of the relationship in regards to whether it was a positive or negative correlation and the significance, but what's the actual probability measure? So and I know that we figured out that the shrub model was the best, but it's always fun to play around with the full model to explore other outputs. So that's what we're going to do right now. So to get this measure of probability or proportion, we calculate what's called an odds ratio. So we'll fit the model using the LRM function, and then we can calculate the odds ratios in R by simply creating a function that codes for such. And we're going to create this function called effect.sizes. So here's the internal coding that's used to create this effect.sizes, which is going to give us the odds ratios. So it's the exponent 1 of the model.lrm and the coefficient of that. Okay, so let me bring up our original model just so we can get the full explanation here. Alrighty, so what we get here from our output of effect sizes are these numeric values according to the predictor variable, and each of these values is the odds ratio. So looking at the original model, we can tell the directionality of the odds ratio. So for instance, for distance, we see that it's not significant, but it is a positive correlation. And the odds ratio is 1.000. So what we can say is that for every 1 unit increase in x, the odds of getting a 1 or having rodents occur in whatever area that we're observing, basically having the presence of rodents, increases, again, we say that because of this positive correlation, increases by 1.000 for distance. At age, we can say something very similar. It's not significant, but we can tell the directionality of that odds ratio. So for every 1 unit increase in X, or for every unit increase in age, the probability of having rodents occur increases by 1.025. And then per shrub, or percent shrub, that is significant. And it also has a positive correlation. So what we can say for that one is for every unit increase in X, or here for every unit increase in percent shrub, the probability of having rodents present significantly increases by 1.102. So that's how you get odds ratios and how you kind of wrap everything up in a nice pretty bow, how you kind of link all of your past outputs with these new outputs. Okay, so let me mess with this thing again. Whee! Okay, so now we can actually plot the log odds ratios, and we're going to do this on the y-axis. So you interpret this by looking at the distance of these gray bands around the blue line. So the closer the bands are, or the tighter this gray area is to the blue line, the better the model. The farther that band stretches, the worse the model. Okay, so here you can see a really nice tight band around the blue line, which makes sense because this is percent shrub, and for percent shrub we found a significant p-value. We can also look at the probability in the same way. So again, same function. You want to see which one has a closer fitting gray band, and that's happens to occur in the percent shrub, and it also follows this distinct logistic regression, which makes sense because percent shrub was significant. So one of the assumptions that we have to test for, so there's 3 assumptions with logistic regression. You have independence, no multicollinearity, and this binomial distribution. So the one assumption we haven't tested for yet is this assumption of no multicollinearity. So we're going to do that by adding interaction terms between the different predictors. So here I am just running 2 models, one that contains an interaction term between percent shrub and age, and this model that says model.all3, which is basically our original model. It just has the normal predictors, no interaction term. But if I was running this for like a real thing, for a real data set, for say my thesis or something, I would have so I would have this model, I would have another model that had an interaction term here, and then maybe clump these together to see what the interaction, if there was an interaction between distance and percent shrub combined interacting with age. You get the gist. But here I'm just testing these 2. Okay, so what we're going to end up doing is using this ANOVA function, and we're testing the model that contains the interaction terms to the model that does not, and seeing if there's significance. So here we get a significant output, which means that the addition of this interaction term significantly influences this model according to the original. So this new model that contains the interaction term is significantly different than our original model, which causes concern for multicollinearity. If there was no significant p-value, then that would say basically by adding that interaction term, it's useless. It's a nonsense variable. But we have significance, so that's concerning. But luckily, we found that our best model was just this RStudio, so we don't have to worry about multicollinearity if we're just running a model with RStudio. So we can run a logistic regression to get the R² value, and we'll just for fun run it on all three. Okay, so you get your p-value, and then what we're really interested in is adjusted R². So this shows that this whole thing, by using these three terms, we're accounting for roughly 44% of the total variation in that full model. And then we can actually plot it if we were interested in seeing the normality of the residuals if we were doing a logistic regression, a linear regression. And that's about it for logistic.